Why do we believe the universe had a beginning? A question that sounds obvious. You've heard that number hundreds of times, 13.8 billion years. It appears in books, in documentaries, in every conversation about the universe. Scientists measure it using the cosmic microwave background radiation discovered in 1965 by Arno Penzias and Robert Wilson. Later, more precise measurements from the Planck satellite made this number accurate to the point where it is almost beyond dispute. So we believe it. Of course we believe it. But this is where things start to get interesting. That number is not just a measurement. It carries a story that there must have been a first moment, an absolute starting point, where everything appeared out of nothing. And if you pause for a moment, really pause and think, then something feels off, not with the number, but with the way we understand it. If you've ever thought of the Big Bang as a giant explosion that happened at some point in space, then I have to tell you, that picture is almost completely wrong. There is no center at all, no place where everything exploded and then spread outward. What we actually observe, starting in 1929, when Edwin Hubble looked at distant galaxies, is that they are moving away from each other in every direction. And that means space itself is expanding. Not matter flying through space, but space stretching itself. Now try doing something simple in your head. Rewind that process. If galaxies are moving apart today, then in the past they were closer together, and the further back you go, the more everything was compressed. Eventually, you imagine an extreme state where the entire universe was squeezed into an incredibly small region, with a temperature not of millions or billions of degrees, but around 1032 Kelvin, a number that defies all ordinary intuition. And then you keep rewinding, getting even closer to what is called the initial moment, about 1043 seconds or Planck time. Here, things start to get strange. The equations of general relativity, which describe the universe very accurately on large scales, begin to produce infinite results. This was analyzed in detail by Stephen Hawking and Roger Penrose back in the 1960s. But when mathematics produces infinities, it usually doesn't mean nature itself becomes infinite. It means our theory has reached its limit. The so-called singularity is not a real object existing somewhere. It is more like a warning sign that our map is no longer valid. So when you hear that we have traced back to the first moment of the universe, I will say no. We have only reached the edge of our knowledge, and we have accidentally mistaken that edge for a real starting point. And if we don't actually see a beginning, then does that beginning even exist? This is exactly when one of the boldest ideas in modern physics appears. In 1983, when Stephen Hawking and James Hartley decided not to fix the singularity, but to completely change the way the question is asked. They proposed something that sounds simple but is actually extremely profound. Perhaps the universe has no boundary, no edge, no starting point. Now, pause for a moment, because this sentence is very easy to misunderstand. This does not mean there is a before the Big Bang that we just haven't discovered yet. On the contrary, it says that the very concept of before may not apply here. And to see that, we have to change the way we think about time, because all our intuition about beginning is based on time running like a straight line. In everyday life, you are used to everything having a cause, then an effect, then another cause, all lined up in a chain stretching back into the past. But the model of Hawking and Hartley says that if you go backward toward what we call the Big Bang, you will not find a point where time keeps going back forever. Instead, time begins to change its nature. It no longer works as a before-after dimension, but gradually becomes more like a spatial dimension. And this is where things get really interesting, because space does not behave the way time does in your head. Let me give you a simpler image, because without an image, this idea is almost impossible to grasp. Imagine you are standing on the surface of the earth. You start walking north. You can keep going through each latitude, each region, until you reach the North Pole. And when you get there, something very strange happens. You cannot go any further north, but not because there is a wall blocking you, not because there is a physical boundary, but because the concept of further north no longer exists at that point. The North Pole is not an edge. It is simply a place where one direction disappears. You can turn in another direction and go south, But you cannot continue in the old direction anymore, because that direction itself has lost its meaning. Hawking and Hartley say that if you look at the universe the right way, what we call the Big Bang is like the North Pole. When you approach it, you do not hit a wall of time. You do not hit a first moment. Instead, you reach a region where time, in the familiar sense, gradually disappears as an independent dimension and merges into the structure of space. It rounds off, just like the surface of the Earth, forming a closed structure with no beginning and no end. This may sound abstract, but its consequences are very clear and very powerful. If time does not stretch infinitely into the past, but instead changes its nature and closes off, then the question, what came before the Big Bang, is no longer a valid physical question. It is like asking, what is north of the North Pole? Our language allows us to ask that question, but nature has no obligation to answer it. And this is the point I find most interesting. In many cases, when we encounter a question that cannot be answered, we think we are not smart enough or do not have enough data. But here, perhaps the problem is not a lack of information. Perhaps the problem is that we are using the wrong type of question. We are trying to impose our everyday intuition on a region where that intuition no longer works. And if that is true, then the entire idea of a beginning of the universe may be nothing more than an illusion created by the way we think, rather than a real feature of nature. Now let's go back to a very familiar word we just used without ever questioning it, the for. It sounds simple, right? Before means something happened earlier, lying behind in the flow of time. But slow down a bit and ask more carefully, what does before actually need in order to exist? It needs a time axis, a dimension along which you can move in the direction of past and future. Without that dimension, the word before is just an empty sound. In everyday life, we never notice this, because time is always there, flowing steadily, making everything seem to have a clear order. But when you approach what we call the Big Bang, in the way Stephen Hawking and James Hartley describe, that very dimension of time begins to change, and eventually no longer exists as an independent dimension. And this is the key point. If time no longer exists, then before no longer exists either. Not because we haven't discovered it yet, but because it does not exist in the physical sense. To see this more clearly, let's go back to geometry, because sometimes geometry says things that language cannot express clearly. Imagine you draw a circle on paper. You can start from any point on the circle and go around it, but you will never find an absolute starting point unless you yourself choose a point as a reference. The circle itself has no starting point. It is simply a closed structure. Or think about the surface of a sphere, like the Earth. You can go in any direction, but there is no edge, no place where the surface suddenly ends. And as we said, you can go north until you reach the North Pole, but there is no further north. The interesting thing is that no one thinks that is a problem of knowledge. No one says, we just haven't discovered what is further north. We accept that this is how geometry works. And what the no boundary model is saying is that the universe at its deepest level may work in a similar way. When you try to apply your ordinary time intuition before, after, cause, effect to that region, you are using the wrong tool. It is like trying to use a flat mat to describe a curved surface. You will always run into contradictions. And this leads to a conclusion that may initially make you uncomfortable. Perhaps the question, what came before the Big Bang, is not a question that has not yet been solved, but a question that has no meaning from the very beginning. And if you feel like we are avoiding the issue, think again. In science, realizing that a question is wrongly posed is sometimes a bigger step forward than finding the answer. When Albert Einstein changed the way we understand space and time, he did not just give nuances, he changed the very type of questions we should ask. And here, we may be standing before a similar turning point. It is not that we lack data about the time before the Big Bang. It is that there is no before to describe. And if that is true, then what we once thought was the limit of our knowledge wall we could not cross is actually a sign that we have reached the true nature of reality. No edge, no starting point, no before. Not because we are not smart enough to find it, but simply because that is the way the universe exists. In classical physics, Everything begins with initial conditions. You want to know what a system will do in the future? It's very simple. You just need to know its state at an initial moment. If I give you a ball and tell you its position, its velocity, and the direction it is moving, you can use Isaac Newton's equations to predict exactly where it will be in a few seconds, a few minutes, or even longer. All of classical mechanics works that way. It is like a movie that has already been filmed, and if you know the first frame, you can play the rest. But notice this, the entire way of thinking depends on there being a first frame. It assumes there is a moment you can call the beginning, where you set everything up and let it evolve. Now, let's go back to the universe. If the universe does not have a real starting moment, if there is no t equals 0 in the physical sense, then what do you do with initial conditions? Where do you put them? You cannot put them before the Big Bang, because as we just saw, before may not exist. You cannot put them at the Big Bang itself, because that is not a normal point in space-time where the equations still work. And so the entire familiar approach of classical physics begins to shake. This does not mean physics is wrong. It means we are trying to apply a tool designed for systems with clear starting points to a system that may not have any starting point at all. And this is where the idea gets interesting. If you do not need initial conditions, then what will replace them? The answer that modern physicists have begun to consider is, perhaps, you do not need to replace anything at all. Perhaps the universe at its deepest level is not a process that starts somewhere, but a self-consistent structure. Let's go back to geometry once more. A circle does not need a starting point to exist. You do not need to choose a special point on the circle to define its entire shape. It exists as a complete whole in which every point is equal. Similarly, the surface of a sphere does not need a starting point to define it. It is simply a closed shape, self-contained, independent of any external conditions. And if the universe is really like that, then we no longer need to ask, how did it begin? The better question might be, how does it sustain itself? This is a very big shift in thinking. Instead of imagining the universe as a machine that was turned on at some moment and then runs forward, you begin to imagine it as a complete system, where every part is connected to the others in a consistent structure. In this view, nothing is started. There is no moment when the laws of physics are switched on. Those laws are part of the overall structure, and the universe exists because the entire structure fits with itself. And if you find this a bit hard to accept, you are not alone. Our intuition always wants a starting point, a first cause, something to hold on to. But physics, time after time, forces us to abandon those intuitions when they no longer fit. And here, we may be standing before a similar transition, from a world where everything needs an initial condition, to a world where the very idea is no longer necessary. And if that is true, then the question, where did the universe begin, is not only hard to answer, but may be the wrong question from the start, because it assumes the universe needs a starting point, while in reality it may never have needed one. If you are still clinging to the idea that everything in the universe must operate like a precise machine, where knowing the initial state alone allows you to deduce the entire future, then quantum mechanics will force you to stop and rethink everything from the beginning. This story begins in 1900, when Max Planck tried to explain what seemed like a small problem about blackbody radiation, and then he was forced to propose a very strange hypothesis. Energy is not continuous, but is exchanged in small, discrete packets. At first, even Planck did not think this would change the entire foundation of physics, but its consequences spread quickly. Scientists like Albert Einstein, Niels Bohr, and Werner Heisenberg began to build a completely new theory, and gradually, the picture of reality we were familiar with began to crack. In the quantum world, particles are no longer tiny points with definite positions. An electron does not exist in a specific place until you measure it. Before measurement, it exists in a state that we can only describe with probabilities. The uncertainty principle tells you that you cannot know both the exact position and velocity of a particle at the same time, not because your equipment is poor, but because nature does not allow it. And this is the most important point. This uncertainty is not a flaw in our knowledge, but a fundamental feature of the world. We are forced to abandon the idea that everything has a clear trajectory and instead accept that nature operates as a set of possibilities. We describe the system with a wave function, which does not give you a single answer, but a spectrum of different possibilities, each with its own probability. When you make a measurement, you do not discover a value that already existed. You force the system to choose one of those possibilities. This may sound uncomfortable because it breaks our intuition about a certain and orderly world. But remember that our intuition was formed from experience at large scales, where quantum effects are averaged out. When you go down to the microscopic level, the world no longer behaves in the way we are used to. And now, let's bring this idea back to the universe. If the basic components of reality are not absolutely definite, then why do we expect the entire universe to begin from a clearly defined state? If an electron does not have a fixed position before measurement, then why must the universe have a single, clear, initial state? Perhaps the whole idea of a definite starting point is a product of classical thinking that we are imposing on a reality that does not work that way. In the quantum view, instead of a single history stretching from past to future, you have a set of possible histories, all existing together in a common description. And this is exactly where everything begins to connect back to what we have said before. If the universe is described by a kind of wave function, then it no longer needs an initial condition in the traditional sense. It does not need a moment when everything is set up and then starts running. Instead, it can be a structure in which all possibilities are summed up into the reality we observe. This does not mean everything is completely random, but that they follow very precise probability rules. The equations of quantum mechanics do not predict specific outcomes, but they predict the probability distribution of outcomes with astonishing accuracy. And this brings us to a conclusion that may initially make you uncomfortable. Perhaps the universe does not need a definite starting point because at the most fundamental level, reality is not built from certain events but from possibilities. And if that is true, then asking what is the initial state of the universe may be like asking what is the exact position of an electron before measurement. The question sounds reasonable, but it assumes there is a definite answer, while nature itself may not provide one. Once you accept that at the most fundamental level, nature does not operate through definite outcomes, but through possibilities, then you are forced to need a way to describe all those possibilities at the same time. And in quantum mechanics, the central tool for doing that is the wave function. It may sound abstract, but think about it in the simplest way. Instead of saying a system is in a specific state, the wave function tells you all the states that the system could have, along with the probability of each state. It does not say, this is what happens, but rather, here is everything that could happen, and here is the likelihood of each one. If you are used to classical thinking, this can make you uncomfortable, because you always want a clear answer, a definite position, a single path. But nature, at its deepest level, seems to have no obligation to provide that. Imagine you do not know where a particle is, and instead of a single point, you have a probability cloud, where some regions have higher probability and some regions have lower probability. Before measurement, that particle is not located at any specific point at all. It exists as the entire cloud, and only when you measure it do you force the system to choose one outcome. This is not due to a lack of information, but the way nature actually works. Now, the next step is the one that makes many people feel uncomfortable, but it is the most logical one. If everything inside the universe is described by a wave function, then why shouldn't the universe itself be described that way? There is no reason to stop at electrons or photons. You can extend this concept to all of space, all matter, all energy, and talk about a wave function of the universe. In this view, the universe is no longer an entity with a single definite state at each moment, but a quantum object that contains all possible configurations of itself. This means that, in a very deep sense, the universe does not have a single history. Instead, it has many possible histories, all existing together in its mathematical description. You can think of it as a set of overlapping possibilities, where each possibility corresponds to a way the universe could evolve. And what we experience, what you and I call reality, is only one branch among them. This does not make the universe vague or unreal. On the contrary, it shows that reality is much richer than what we directly observe. One of the most important consequences of this view is that it completely undermines the idea of a single initial state. A wave function does not need a starting point in the classical sense. It does not need a moment when everything is set up and then begins to operate. It exists as an overall description of the entire system, including all possibilities at once. This means you do not need to ask, how did the universe begin, in the way you ask, how did the ball start moving? Those two questions belong to two completely different ways of describing things. In classical physics, you need initial conditions because you are describing a system that evolves over time. But in a global quantum description, you are describing the entire system as a single structure without needing a separate starting point. And this is the point where everything begins to connect back to what we have said about the no-boundary proposal. If time does not stretch infinitely into the past, if it rounds off and becomes part of the structure of space, then finding a first moment becomes unnecessary. Instead, you have a wave function that describes that entire structure, a structure with no edge, no starting point, but still complete. This also explains why we observe an orderly universe. Not all possibilities have the same probability. The quantum equations allow us to calculate the probabilities of different configurations, and some configurations are more stable and more likely to appear. Those are the configurations that make up what we call the real universe. And if you feel that this makes reality strange, you are completely right. But the history of physics has shown that every time we go deeper, reality always becomes stranger, not simpler. And what matters is not whether it fits our intuition, but whether it fits what nature actually does. When you look at the universe through the lens of the wave function, the idea of a single starting point gradually loses its meaning, not because we have found a before, but because we realize that there may never have been a need for a before in the first place. The idea I introduced in the 1940s, often called the path integral, comes from a very simple question. If a particle does not follow a single path, then how does it really go? The answer that quantum physics gives is not to choose a specific path, but something that sounds crazy. It goes along every possible path, not in the sense of one after another, but all at once in the mathematical description. This is not just a different way of phrasing things, but a fundamental change in the way we understand reality. Instead of a linear sequence of events starting from a point, we have a network of possibilities, all existing and interacting together. And from that network, what we call real history emerges as the result with the highest probability. When you look at it this way, the universe no longer resembles a story with a beginning, climax, and ending, but a comprehensive mathematical structure where every possibility is taken into account. And in such a structure, asking what happened before everything may no longer be the right question, because there is no single timeline to trace back to a starting point. Instead, there is a set of histories, and it is that set itself that truly exists. When you look at the universe from the perspective that every history contributes, and there is no single path chosen from the beginning, then the idea of a time zero begins to become unnecessary. In classical physics, you always want a clear starting point, a moment when you can set all the initial conditions, and then let the equations run forward. But in the picture we are building, that is like trying to find the first point on a perfect circle. You can choose any point and give it special meaning, but the truth is that the structure of the circle does not require such a point to exist. It is complete from the start, not in the sense of time, but in the sense of structure. And this is the most important thing you need to grasp. The absence of t equals 0 is not a flaw in our understanding, but possibly a sign that we are looking at the nature of reality in the right way. Let's go back to the idea of the path integral because it is one of the clearest tools for seeing this. When you calculate in quantum mechanics that way, you do not start from a single state and then let the system evolve. You do not say, this is the starting point and everything will go from here. Instead, you consider all possibilities, all the paths the system could take, and you add them up to obtain the final result. No single path is prioritized from the beginning. No history is chosen as real before you calculate. The reality you observe is the result of that entire sum. And in such an approach, there is no room for a special moment playing the role of an absolute beginning. The entire structure is defined as a whole. not step by step from an initial point. When you extend this idea to the entire universe, something very interesting begins to appear. When you want to calculate the probability that a particle goes from point A to point B, you do not just consider a straight line or an optimal trajectory. You have to add up the contributions from every imaginable path, from those that are almost straight to those that are winding, even extremely bizarre ones. Each path contributes a part, and when you add them all together in a very specific way, you get the correct result that experiments confirm. This may sound like a mathematical trick, but it actually reflects the way nature works at its deepest level. There is not a single history that is chosen from the beginning. There is a sum of countless possible histories, all participating in creating the final result. When you look at a particle and see it at a specific position, that is not because it followed a definite path from the start, but the result of interference between all the paths it could have taken. And now, let's do what we did before with the wave function. Extend this idea to the entire universe. If a particle can be described as the sum of every possible history, then why can't the universe be described in a similar way? In this view, the universe does not have a single history stretching from the past to the present. Instead, it has countless possible histories, each corresponding to a way that space and time could evolve. And what we call the history of the universe is actually only a part of that whole, a result that stands out from the combination of all possibilities. This completely changes the way you think about origins. Instead of asking what happened first, you begin to ask, what does the set of possible histories look like? You no longer look for a single path leading to the present, but look at the entire space of possibilities and how they interact with each other. And this is the point that connects directly to what we have said about the universe having no boundary. In the path integral approach, you do not need to specify a single initial state to begin the calculation. Instead, you consider all possible configurations of space-time, including those with no boundary, and you sum up their contributions. Some configurations will contribute more strongly, some more weakly, and the final result is what we observe. This means that the universe we see is not the result of a single initial choice, but the result of the sum of countless possibilities. And if you go back to the original question about the beginning of the universe, you will see it starting to lose its meaning. In a picture where every history exists in the description, finding a first history becomes unnecessary. It is like asking, in a complex harmonic piece of music, which note is the first note that decides everything. The entire piece exists as a whole, and every part contributes to the overall structure. Perhaps the universe does not need an initial state to exist, because it is not a process that begins and then moves forward, but a self-consistent structure. This may sound abstract, but you have already seen a similar idea in mathematics without realizing it. An equation does not need a starting moment to have solutions. It has solutions because its structure allows those solutions to exist. Those solutions do not appear at some moment. They exist as an inevitable part of the logical system to which the equation belongs. And if you look at the universe in a similar way, you begin to see that it may exist not because it was turned on at some moment, but because its entire structure is consistent. Space, time, matter, and energy are not things assembled from a starting point, but parts of a whole, linked together in a way that does not require an external cause to activate them. This also explains why the search for a first cause becomes increasingly difficult as you go deeper into physics. In a system defined by global self-consistency, there is no room for an external factor to play the role of starting everything. You do not need something to turn the universe on, just as you do not need a special point to start a circle. The circle exists because it is a closed structure, and if the universe is also a closed structure in a much deeper sense, then the question, when did it begin, may no longer be an appropriate question. This does not mean that time does not exist. Time is still part of our experience and physical description, but the way we understand it needs to change. Time in this picture is not an axis stretching infinitely into the past with a clear starting point. It may be part of the overall structure, possibly having shape and limits in ways that our intuition formed from everyday experience does not easily grasp. And once you begin to accept that, the idea of a first moment gradually loses its appeal. not because we have replaced it with a more specific answer, but because we realize that there may never have been a need for such an answer in the first place. What really matters is no longer finding t equals 0, but understanding how the entire universe can exist as a self-organizing system, a structure in which every part supports the others, without needing an absolute starting point as a foundation. And when you look at it that way, the question of the beginning does not disappear, but it changes its form from a point in time to a question about the structure, reality. If you accept that the universe may have no edge, no boundary where everything ends, then another question immediately arises, and it is not simple at all. So why does the universe look like this? Why, on large scales, is it almost uniform in every direction? Why is its geometry almost flat, instead of strongly curved as you might expect from such a complex structure? These are not small details, but were once major mysteries in cosmology for many decades. And it is right here, in 1980, that an extremely bold idea was proposed by Alan Guth. An idea that does not directly answer the question, how did the universe begin, but focuses on a different, more subtle but equally profound question: why does the universe have the shape and structure that we observe? That idea is called cosmic inflation. And what it proposes truly changes the way we look at the entire story. Instead of a slow and steady expansion as we see today, Guth proposed that in an extremely short period after the initial phase that physics can still describe, the universe underwent an extremely violent phase of expansion. Not linear expansion, but exponential expansion, where the size of space doubles and doubles again, repeating at a dizzying rate. The time during which this process occurred is almost impossible to imagine, only from about 1036 to 1032 seconds after the initial phase. But in that extremely short time, the change was enormous. A region of space so small it was almost microscopic could be stretched into a region larger than the entire observable universe today. This is not just an interesting detail. It directly solves problems that previously seemed to have no solution. For example, why does the universe look almost the same in every direction, even though regions very far apart seem to have had insufficient time to communicate with each other? Inflation shows that those regions were once very close together before being stretched apart, so they could have reached a state of equilibrium before being separated. Or the problem of curvature. Why is the universe almost flat? If you take a curved surface and stretch it strongly enough, it will look increasingly flat on the scale you observe, just like the way the surface of the Earth looks flat when you stand on a vast plain. Inflation does exactly that with space-time, smoothing out the initial curvatures and creating a universe with nearly Euclidean geometry that we measure today. But what is truly interesting is not only in solving the observational problems, but in the way this idea connects with the entire story we have been through. Inflation does not require a sharp starting point in the classical sense. It does not need a moment when everything is perfectly set up and only then begins to operate. It only needs a sufficiently special initial state of configuration of quantum field energy to trigger that rapid expansion process. And from there, the rest of the universe can form naturally. When you combine this with the idea of a universe with no boundary and the quantum description, you begin to see that the beginning is no longer a clear point, but more like a fuzzy region where different descriptions intersect with each other. There is no sharp boundary between before and after, but rather a transitional process in which our familiar concepts gradually lose their meaning. Inflation also brings an even deeper consequence. If a very small region can expand into a gigantic universe like the one we observe, then there is no reason to believe that this only happened once. There could be countless other regions with similar or different conditions that also went through this process. This opens the door to the idea of a multiverse, where there is not just one single universe, but possibly countless different universes, each the result of its own inflation phase. Each region could have slightly different physical constants, different structures, different histories. And our universe is just one of them. But even if you do not go as far as fully accepting the multiverse idea, inflation alone has already changed the way you look at reality. It shows that the features we observe, the uniformity, the flatness, the large-scale structure, do not need to have been designed from the start. They could emerge naturally from the dynamics of space-time, from simple laws operating under extreme conditions. And this brings us back to the central point of the entire journey. Perhaps the universe does not need a clear starting moment, not because we have not found it yet, but because what we see could be generated from the internal processes of the universe itself. Inflation does not solve the entire question of origins, but it strongly undermines the idea that there must be a special starting point where everything was perfectly set up. Instead, it shows that a very large part of the structure we observe could arise from simple laws operating over an extremely short period of time, yet leaving an imprint that lasts for billions of years. And when you look at it that way, the beginning is no longer a single moment, but becomes a process, a transition, something much softer than what our initial intuition once imagined. What makes this story even stranger is that inflation, as Alan Guth originally envisioned it, may not be a one-time event that ends neatly as we usually imagine, but may be a process that never really stops. As physicists continued to develop and refine this idea in the years that followed, they began to realize something very important. In many models, inflation does not end simultaneously everywhere in space. There is no single global moment where the entire universe switches from the inflationary state to the normal state at the same time. Instead, the process occurs unevenly. In some regions, inflation stops. Energy is converted into matter and radiation, and from there, a universe like ours forms, where elementary particles appear, atoms form, stars shine, and galaxies evolve over time. But in other regions, inflation does not stop. Space there continues to expand at an extremely fast rate, continuing to stretch its own structure and creating conditions for new regions to break off. And it is from this realization that a very powerful idea was born: eternal inflation. Try to imagine a surface that keeps inflating, like an elastic sheet being continuously stretched. On that surface, at random points, small bubbles form, breaking away from the extremely rapid expansion state and becoming more stable regions. These bubbles no longer expand in the violent way the rest does, but begin to evolve according to the familiar laws of physics that we know. But the important thing is, while those bubbles form and develop, the rest of the surface continues to expand. The process does not stop, does not slow down, and shows no sign of ending. The result is a structure in which stable regions, the bubble universes, appear scattered across a background of space that is expanding non-stop. Each such region can function as a separate universe, with its own initial conditions, its own physical constants, and its own evolutionary history. What is remarkable here is not the enormous number of universes that could exist, but the nature of the process that creates them. This is not an event with a clear beginning and end, but a continuous process with no limits in the ordinary sense. There is no moment when you can say that inflation has completely ended. On a global scale, it is still continuing, and according to many models, it will continue like this forever. And this has a very profound consequence for the way we think about the origin of the universe. If the process of creating universe regions is eternal into the future, then there is no obvious reason to assume that it must have had a sharp starting point in the past. In some models, time may stretch infinitely in some sense, or at least there is no marker that you can identify as the first moment of everything. This further undermines the idea that there must exist a single beginning, a special moment where all of reality was set up. The background space is boiling in the quantum sense, and in that process, universe bubbles form. Each bubble is a universe with its own Big Bang, with its own history. Our universe may be just one of those bubbles, no more special, no more central than any other bubble. This has a very strong consequence. The Big Bang we observe is not the beginning of everything, but only the beginning of the specific region in which we live. Just like a bubble in a pot of water is not the beginning of the entire boiling process, but only a local manifestation of it. And what makes this idea profound is that it is not just philosophical speculation, but comes directly from the physical models of eternal inflation. When you combine quantum mechanics with the extremely rapid expansion of space, the natural result is a branching structure where different regions break off and evolve independently. This also helps explain why our universe has very specific properties, such as physical constants with values precise enough to allow stable matter and life to exist. In a multiverse, there is no need to assume that those values are unique or designed. Instead, there may exist countless regions with different values, and we simply happen to be in a region where the conditions allow us to exist. But what is more important for our story is the way this idea completely changes the view of the beginning. If countless universe bubbles are being created continuously, then finding an absolute beginning for all of them becomes like asking which bubble in the pot of water is the first bubble. There may be an answer in a specific model, but it is no longer the central question. What matters is understanding the process that creates the bubbles, rather than identifying one particular bubble as first. And when you look at it this way, you begin to see that the entire concept of a beginning may have been misplaced from the start. We are used to thinking that there must be a point where everything begins. But in a branching structure like the multiverse, beginning is no longer a point, but a process. A process that may have no single starting point, but is instead a network of events continuously creating new regions. And if that is true, then the question, when did the universe begin, may need to be replaced by a completely different question. What structure allows universes like this to appear? This does not make the story simpler. On the contrary, it expands it to a scale that our intuition struggles to keep up with. But at the same time, it also brings a deep consistency. From quantum mechanics to the path integral to eternal inflation, everything points in the same direction. That reality is not a straight line starting from a point, but a large structure where many possibilities coexist and are continuously being realized. And in such a structure, finding a single beginning may no longer be necessary. You may have heard this number before, but I want you to really pause and think about it. Our observable universe has a diameter of about 93 billion light years. Not 93 million, not 93,000, but 93 billion light years. That means light, the fastest thing we know, traveling at about 300,000 kilometers per second, still takes tens of billions of years to go from one end of the region we can observe to the other. And remember this, because it is very important. That is not the size of the entire universe, but only the part we can see. It is limited by the time that light has been able to travel to us, since the universe became transparent after the Big Bang. Beyond that region, there may be much more, possibly infinite, possibly structures we have never imagined, but we have no way to directly observe them. And when you connect this with the idea of eternal inflation in the multiverse we just discussed, the picture becomes much larger. Our observable universe may be only an extremely small part of a larger bubble, and that bubble itself may be just one of countless other bubbles existing in a process of expansion that never stops. This means that everything you have ever known, every galaxy that telescopes can see, every star, every planet, every form of life may be only an extremely small slice of a much larger reality. If you feel that this makes humans seem tiny, you are not wrong, but this is not the first time science has led us to that conclusion. When Nicolaus Copernicus pointed out that Earth is not the center of the universe, we had to give up a special position. When Charles Darwin showed that humans are not a separately created entity, but the result of evolution, we had to give up another layer of familiar meaning. And now, modern physics is pushing us even further. Not only are we not at the center, but perhaps even the universe we observe is not the whole picture. But the interesting thing is that this does not really diminish our significance. Instead, it changes the way we understand significance. It says that reality is much larger, deeper, and more complex than what our intuition once allowed. And that brings us back to the question we have been pursuing from the beginning. Does the universe need a beginning? If what we call the universe is only a small part of a larger structure, then searching for an absolute beginning within our observable range may be the wrong approach. It is like standing on a small island and trying to find the starting point of the ocean by looking at the horizon. What you see is limited by your position, not by the nature of the entire system. And once you realize that, you begin to see that the original question needs to be expanded. Not when did our universe begin, but does the entire structure of which we are a part need a starting point or not? And when you ask the question that way, all the ideas we have been through, the wave function, the path integral, no boundary, eternal inflation, begin to connect into a unified picture. There is no clear indication that a single first moment must exist. Instead, everything suggests that reality may be a large structure, where what we observe is only a very small part, a local slice in a much larger system. And in such a system, searching for an absolute starting point may not only be difficult, but may no longer be the right question. Once you get used to the idea that what we observe is only a very small part of a larger structure, the Big Bang starts to look completely different from the way it is usually described. We are used to thinking of the Big Bang as the first moment of everything, as a point where the entire universe suddenly appeared out of nothing. But if our universe is only a bubble in a larger process, then the Big Bang may not be the beginning of everything, but only the beginning of the specific region in which we live. One way to understand this is to think about phase transitions in physics, processes you can see right in everyday life. Imagine water changing from a liquid state to a vapor state. When water boils, you do not say that steam is the beginning of everything, but you understand that it is a phase transition occurring within a larger system. Water existed before that, only in a different state. And when the temperature reaches a certain threshold, a part of the system transitions to a new state, creating the steam bubbles you observe. Something similar may be happening with the Big Bang. Instead of being an event that creates all of reality out of nothing, it may be a phase transition in the deeper structure of space-time. Some region of space undergoes a sudden change, leading to rapid expansion, forming matter and energy in the way we observe. And that region is our universe. But that does not require all of reality to begin at the same moment. It only requires that within a larger structure, there are regions that can undergo such phase transitions. When you look at it this way, the Big Bang is no longer a single special point, but a type of event that can happen many times in many different places within a broader context. This fits very naturally with the idea of eternal inflation, where regions of space continuously break off and evolve independently. Each region can have its own Big Bang, just like each bubble in a pot of boiling water has its own moment of formation. And just as you do not ask which bubble was the first one that decided everything, you also do not need to find a single Big Bang for all of reality. In that state, the concept of distance and time, in a certain sense, loses its absolute scale. And Penrose proposes that this final state can be mathematically transformed to become the initial state of a new universe. In other words, what we call the end of one universe can simultaneously be the beginning of another universe, but without needing a starting point in the traditional sense. This creates a chain of universes following one another, with no first point and no final point, only continuous transitions between states. And if you look back at all these models, eternal inflation, the multiverse, the cyclic universe, conformal cyclic cosmology, you begin to see something very interesting. Although they differ greatly in details, mechanisms, and mathematics, they all converge on one common idea. There is no need for an absolute beginning to explain the existence of the universe. This does not mean we have the final answer, because each model still has open questions and unresolved issues. But it shows that within the framework of modern physics, abandoning the idea of a single starting point is not only a possibility, but a very natural direction. And this brings us back to our initial intuition. We are used to everything having a cause and a starting point, because that is how the world works on the everyday scale. But when you expand your view to the cosmic scale, those rules may no longer apply in the way we expect. Perhaps reality is not a story with a first chapter, but a structure or a process that does not need a starting point to exist. When you put all those models side by side and realize that none of them actually requires an absolute beginning, a familiar question begins to shake. And that is a question humans have asked for thousands of years. What is the first cause? We are used to thinking that everything must have a cause. A stone falls because of gravity. A ball moves because you threw it. An event happens because another event happened before it. This chain of cause and effect seems to be the foundation of how we understand the world. But pause for a moment and ask more carefully, what does cause actually need in order to exist? The simple but very important answer is, it needs time. To say that A is the cause of B, you must have an order, where A happens before and B happens after. If there's no concept of before and after, then the concept of cause begins to lose its meaning. And this is exactly the point where everything connects back to what we have said before. If time does not exist in the ordinary sense, near what we call the Big Bang, or if it rounds off, as in the no-boundary model, then you cannot simply apply the cause and effect chain as in everyday life. Asking what caused the Big Bang may be like asking what is north of the North Pole. Instead, you have a completely different picture, a process that is ongoing, where new regions are continuously being born, where what we observe is only a very small part of a much larger system. When you connect this with what we have said about the wave function and the path integral, everything begins to fit together in a very natural way. The universe is no longer an event that begins at a point, but a process in which many possibilities are realized in different ways. Eternal inflation provides a concrete physical mechanism for that, a way for quantum possibilities to branch off into separate regions that we can call universes. And this also helps explain something very basic about our experience. Why we do not see the entire structure. We are limited to an observable region, a small bubble in a much larger space. Regions outside are stretched away at such a fast rate that light from them can never reach us. So from our perspective, the universe we see appears to be all that exists. But from a broader perspective, it may be only an extremely small part of a much larger process. A process with no clear starting point and no ending point either. And if you go back to the original question, whether the universe needs a beginning or not, then eternal inflation offers a very strong suggestion. Perhaps not. Perhaps what we call the Big Bang is only a local event, a transitional phase in a much larger process, where searching for an absolute starting point is no longer the appropriate approach. When you push the idea of eternal inflation one step further, an even larger picture begins to emerge. And that is where the concept of the multiverse appears almost inevitably. If space continues to expand in some regions while in others the process stops and freezes into stable universes, then what you have is no longer a single universe, but countless universe regions existing in parallel with each other. Each such region could have its own history, its own structure, and even different physical constants. But to understand this without getting lost in overly abstract concepts, let's go back to a very familiar image, boiling water. When you boil a pot of water, you do not see the entire water turning into steam uniformly at the same time. Instead, you see small bubbles forming at different points, then growing, breaking off, and rising to the surface. Each bubble is a separate region, formed from the same environment, but with its own development process. Now imagine that space works in a similar way. What matters is understanding the mechanism that allows such events to occur. And when you return to the quantum models, you see that these phase transitions are not events that are switched on by an external cause, but can arise naturally from the fluctuations of quantum fields. Space is not completely empty, but can contain background energy, and under certain conditions, that energy can transform into a new state, leading to the expansion we call the Big Bang. This further reinforces the idea that the Big Bang is not an absolute beginning, but a manifestation of a deeper process. And if that is true, then the question, what came before the Big Bang, needs to be replaced with a different question. What was the state before that phase transition, and how does it exist within the overall structure? This does not make the story simpler. On the contrary, it makes it much richer, but at the same time, it is also more consistent with what we have seen. There is no clear evidence that an absolute starting point must exist. Instead, everything points to the possibility that reality may be a system in which events like the Big Bang occur as local phase transitions within a broader context that we are only beginning to understand. When you start to see the Big Bang as a local event rather than an absolute beginning, the interesting thing is that you are no longer bound to a single explanation. And this is when many different models in cosmology begin to appear, each trying to answer the same question in very different ways, but sharing a remarkable common point. None of them requires an absolute starting point. One of the prominent models is the cyclic universe model, developed by Paul Steinhardt along with his collaborators. In this view, the universe is not a one-time event that continues forever, but a series of cycles, where the universe expands, then contracts, and then bounces back in a new cycle. The Big Bang in this model is not the starting point of everything, but only the transition point between two cycles. Just like sunrise is not the beginning of time, but the transition between night and day. This has a very important consequence. If this cycle follows another in an infinitely long chain, then there is no reason for a first cycle to exist. The universe, in that sense, may have always existed in some form, changing its appearance but without needing an absolute starting point. But this is not the only way to think about the problem. Another idea, even bolder in some sense, comes from Roger Penrose with the conformal cyclic cosmology model. In this model, the universe does not simply repeat in simple cycles, but each cycle of the universe, called an aeon, is connected to the next in a very special way. When the universe expands long enough, all large structures like galaxies, stars, and even massive particles gradually disappear or decay, leaving a state that is almost only massless energy. The question sounds reasonable, but it assumes a structure, a timeline stretching into the past that may not exist in that region. And if you think this is just a way to avoid the question, then consider again how we use the concept of cause in other fields. In modern physics, especially in quantum mechanics, the relationship between cause and effect is not always as clear as we think. There are phenomena that we can only describe with probabilities, not with a definite chain of causes. And when you go further into cosmological models, the concept of cause may need to be replaced by something else, such as the self-consistency of the entire system. Instead of asking what caused the universe, you may have to ask what structure allows the universe to exist consistently. This is a very big shift because it moves the focus from a linear chain of events to an overall structure. It is like no longer asking which edge of the sphere appeared first, but instead understanding that the entire sphere exists as a complete entity, independent of the temporal order of the points on it. This does not mean that cause does not exist in every circumstance. At the scale where we live, where time flows in a clear direction, cause and effect remains an extremely useful and accurate concept. But when you push the question to the boundaries of the universe, where the very concept of time becomes blurred, then applying the concept of cause directly may no longer be appropriate. And this is the most important point. If cause requires time, and time does not exist in the way we think before the Big Bang, then searching for a first cause may not be a meaningful question in physics. It is not a question without an answer, but a question posed within a framework that no longer applies. And if you feel this makes the story harder to grasp, you are not wrong. But at the same time, it also makes the picture more consistent with everything we have seen. There is no clear starting point, no edge, no before, and therefore perhaps no first cause either. Instead, there is a structure in which the laws of physics, space, and time coexist in a self-consistent way. And in such a structure, the question, why does the universe exist, may need to be understood differently, not as a chain of causes leading to a result, but as a property of the structure itself. When you start to doubt the concept of a first cause, another unusual idea often appears right after, and it may be even more uncomfortable. What does nothing really mean? We often say that the universe must have appeared from nothing, as if nothing is a clear state, a completely empty background from which everything pops up. But pause and think seriously about that. Does nothing really exist as a physical state, or is it just a linguistic concept we use when there is nothing to describe? In modern physics, especially quantum mechanics, the vacuum is not a completely empty void. It is not an empty, silent space where nothing happens. On the contrary, it is one of the most dynamic states we know. In what we call the quantum vacuum, the fundamental fields still exist, and they are never completely still. Quantum fluctuations continuously occur, creating and annihilating particle-antiparticle pairs in extremely short periods of time. These particles appear and disappear almost immediately, but their effects can be measured. This is not speculation, but something that has been confirmed through effects like the Casimir effect and other experiments. This means that what we call emptiness is actually not empty at all. It is a background full of energy and activity at the deepest level. And if that is how the vacuum works, then the idea of nothing begins to fade. Because to have a quantum vacuum, you still need the laws of physics, the fundamental fields, and a structure in which those fluctuations can occur. So what would nothing really be? A state with no space, no time, no laws, no fields, nothing at all. But as soon as you try to think about that state, you realize you have no tools to describe it. No equation applies, no concept retains its meaning. And this leads to a very interesting possibility. Perhaps nothing is not a stable state from which the universe can begin. Perhaps it simply does not exist as a physical possibility. Meanwhile, something, a structure with laws, with quantum fields, with the possibility of fluctuations, is the more natural state. If you look at it this way, the question, why is there something rather than nothing, begins to change its meaning. Perhaps it is not something that needs to be explained, but nothing itself that cannot exist. And if that is true, then the universe does not need to be created from nothing, because nothing is not a viable foundation from the start. This also connects with what we have said about the self-consistency of the universe. If the universe is a structure that the laws of physics allow to exist consistently, then it can exist without an external cause. Not because we have found the cause, but because the concept of cause may not apply at that level. And once you accept that the quantum vacuum is not really empty, that nothing is not a simple state, then the entire story of the origin of the universe begins to change. Instead of imagining a moment where everything appears from nothing, you begin to see a reality where possibilities have always existed, where fluctuations can create structure, and where existence itself may be the natural state. This does not make the question easier, but it makes it more precise. And in science, sometimes rephrasing the question correctly is more important than finding the answer immediately. And when you start to see that nothing does not really exist in the physical sense, then another question arises almost immediately. If the universe does not need a beginning, then why do we still perceive time as if it has a very clear direction, a past behind us and a future ahead? Why do we not see time running backward? This is exactly where the concept of entropy comes in, and it changes the way you understand time more profoundly than anything before it. Entropy, put simply, is a measure of the level of disorder, or the number of microstates that a system can have. This idea was developed by Ludwig Boltzmann in the 19th century, and it leads to a very strong conclusion. In an isolated system, entropy tends to increase over time. This means that natural systems tend to go from ordered states to less ordered states. Think of a hot cup of coffee left in a room. It will gradually cool down over time, with heat dispersing into the surrounding environment. You never see the reverse happen, where heat from the air spontaneously concentrates to heat up the cup of coffee. Not because it is absolutely forbidden, but because its probability is extremely low. And this is the key. The arrow of time does not come from the fundamental equations of physics, because most of those equations work the same in both directions of time, but from probability. There are far more disordered states than ordered ones, so the system tends toward disorder. This creates the feeling that time has a direction. But now let's connect this to the universe. If entropy tends to increase, then that means in the past entropy must have been lower. And this is one of the deepest questions in cosmology. Why did the early universe have such low entropy? Why did it start in a very ordered state that allowed structures like galaxies, stars, and life to form? This is not a small detail, but a necessary condition for us to exist and ask this question. But what is interesting is that this does not necessarily mean there was an absolute starting moment. It only means that in the portion of history we observe, entropy has increased from a low value. In the models we have discussed, no boundary universe, eternal inflation, multiverse, the low entropy state can emerge as part of the overall structure without needing to be placed at a single starting point. For example, in a multiverse, there may be regions where low entropy arises due to quantum fluctuations, and it is precisely those regions where complex structures can form. This means that the arrow of time we experience may be a local feature, not a global feature of all reality. And if that is true, then the time we perceive with a clear direction from past to future may be only part of the story, not the whole story. This brings us back to our original idea. Perhaps the universe does not have an absolute beginning, but only regions and phases where low entropy creates the feeling of a starting point. And when you look at it that way, the arrow of time is no longer evidence for an absolute beginning, but a sign of how states with different probabilities are distributed in the universe. It is the result of statistics, not of a special event. And this leads to a very interesting conclusion. Time, in the way we experience it, may not be a fundamental element of reality, but an emergent phenomenon arising from the way physical states are arranged and evolve. And if time is not fundamental, then searching for a first moment may no longer be the right way to understand the universe. Going through all these ideas, from the possibility that time has no before, from the absence of initial conditions, from the coexistence of many histories, from the idea that the Big Bang is only a local event, and even from the idea that nothing may not be a real state, a completely different view of the universe begins to emerge. And it may be the most radical one: the universe as a mathematical structure. This does not mean the universe is just numbers or equations written on paper, but that the laws and mathematical relationships do not merely describe the universe, but may actually constitute it. Throughout the history of physics, from Isaac Newton to Albert Einstein, we have seen that mathematical equations are not just convenient tools, but seem to reflect a deep structure of reality. Those equations are not merely approximate. Many times they are accurate to an astonishing degree, predicting phenomena we had never observed before. This suggests a very strong possibility. Perhaps reality does not exist first, and then we find mathematics to describe it. But mathematics itself is the foundation, and the universe is one of the ways that structure manifests. If you look at it this way, then the question, when did the universe begin, starts to lose its meaning, in the same way as asking, where does a mathematical theorem begin? A theorem does not have a starting moment. It exists as a necessary consequence of axioms and logical rules. You may discover it at some point, but it does not appear at that moment. It has always existed within the mathematical structure to which it belongs. And if the universe is like that too, then it does not need a starting moment. It exists because it is a consistent structure, a configuration that the laws allow to exist without contradiction. This connects very closely with the idea of self-consistency we talked about earlier. Instead of needing an external cause to create the universe, its own structure may be sufficient for it to exist. Just like a circle does not need a starting point to exist, a mathematical structure does not need a creation event. It simply is. And if you feel this seems too abstract or too philosophical, remember that modern physics has repeatedly led us to similar conclusions. When you describe the universe with quantum equations, with fields and wave functions, you are working with mathematical objects. And those objects do not need a moment in time to exist. They are relationships, structures, and from those structures, what we call physical reality emerges as a specific manifestation. This also helps explain why the laws of physics seem fine-tuned in an astonishing way to allow complex structures and life to exist. In a picture where many mathematical structures can exist, we only observe those structures compatible with the existence of observers. But what is more important is that, in this view, there does not need to be a moment when the laws are established. The laws do not appear over time. They are part of the overall structure. And if the universe is a manifestation of such a structure, then asking when did it begin may be like asking when does an equation become true. It does not become true at a moment. It is true because its structure is that way. And this leads to a very powerful idea that may be a bit hard to accept at first. The existence of the universe may not be something that needs to be explained by a cause, but a necessary consequence of a consistent structure. Not why is there something, but something exists because it can exist without contradiction. And when you look at it that way, the entire question of a beginning begins to dissolve. Not because we have found a first moment, but because we realize that there may never have been a need for such a moment in the first place. A long journey like this often makes people expect a clear answer at the end, a neat conclusion to wrap up all the ideas that have been covered. But if there is one thing physics teaches us, it is this: the deepest questions rarely end in the way you expect. We started with a number that seemed certain, 13.8 billion years, a number so precise that it made you believe you were standing on solid ground. Then we realized that the Big Bang was not an explosion in space, but the expansion of space itself. And when we rewound, we did not find a first moment, but only touched the limit of the theory. We went further to the idea that time may not exist in the way we are familiar with, near what is called the beginning, that before may have no meaning. that the universe may have no boundary, just like the surface of a sphere. We abandoned initial conditions, accepted that reality at the deepest level is not deterministic but probabilistic, that the wave function describes many possibilities coexisting, that every history contributes to what we observe. We saw that there is no need for a time zero, that the universe can be self-consistent like a closed structure. We expanded the picture with inflation, with eternal inflation, with universe bubbles continuously forming, and realized that what we call the universe may be only a very small part of a much larger reality. We began to see the Big Bang as a local phase transition, not the beginning of everything, and saw that there are different models, cyclic, conformal, cyclic, and all allow a universe without an absolute starting point. We reframed the question of cause, realizing that cause requires time, and if time does not exist in the way we think, then a first cause may not be a meaningful concept. We examined nothing and saw that it may not exist as a physical state, that the quantum vacuum is not empty at all, that fluctuations are always present. We understood the arrow of time as a consequence of entropy, not evidence for a beginning, but a local feature of how states are distributed. And finally, we arrived at a view where the universe can be seen as a mathematical structure, a self-consistent system that does not need a starting moment to exist. If you look back at the entire journey, you will see one thing very clearly. Each step forward did not bring us closer to a first moment, but gradually made the idea of such a moment unnecessary. And this is not a failure of science, but possibly a sign that we're getting closer to the right understanding, because science is not only about finding answers, but also about learning how to ask the right questions. And perhaps the question, when did the universe begin, is not the right question. Perhaps it carries assumptions that reality does not share, but that does not mean we have understood everything. Not at all. We still do not have a complete theory that combines quantum mechanics and gravity. We still do not fully understand the nature of space-time. We still do not know whether the models we build reflect ultimate reality or only good approximations within a certain range. And it is precisely that which makes the story interesting. Because every time we think we are close to the answer, nature opens up another deeper layer, a new question, a new perspective. And perhaps that is the most important thing you can take away from this journey. Not a definite conclusion, but a change in the way you look at the question. Not, where did the universe begin? But does the concept of a beginning even apply here? And if you have to leave with one single thought, then perhaps it would be this. Perhaps the universe has no beginning. Or perhaps we are simply asking the wrong question. If you find that this perspective changes the way you think about the universe, please subscribe to the channel to continue exploring even deeper questions with me. Thank you for watching, and see you in our next journey.